Welcome all. In last lecture we have seen clocked D flip-flop. In today's lecture we are going to see the clocked JK flip-flop, which is also called as a edge triggered JK flip-flop. It can be of two types: positive edge triggered JK flip-flop and second is negative edge triggered JK flip-flop. Now first we will see the positive edge triggered JK flip-flop. This is the circuit diagram of positive edge triggered JK flip-flop, which is formed by a SR flip-flop. The only difference is that the NAND gate 3 and 4 are having three inputs. One is a clock input, which is given through this differential circuit, which will provide the positive clock edges as the flip-flop is positive edge triggered one. Another second input is this J input and this one is the K input. Third input to this NAND gate 3 is the inverted output of this flip-flop, that is Q complement, is given as an input, and third input to the NAND gate 4 is the normal output, that is Q, is given as an input to this fourth NAND gate. And this NAND gate 1 and 2 forms the basic SR latch, which we have already studied. This differential circuit CR1 and a rectifier circuit DR2 provides the positive spikes at point A, that is clock input, and the negative spikes are blocked by the diode, which is a forward biased diode. Now referring to this figure, we can write the mathematical expression of this R dash and S dash, by which we will come to know what are the end outputs of the JK flip-flop. So the expression for R dash will be the inputs to the NAND gate 3 are J, Q complement and a clock input. Therefore R dash expression will become J into Q complement into clock and its whole complement. Whereas the S dash is the output of NAND gate 4, to which the three inputs are K, Q and the clock. Therefore expression for S dash will be K, Q clock in its complement. This is the symbol of the positive edge triggered JK flip-flop, which is having two inputs J and K, two outputs Q and Q complement, and one clock input, and this symbol shows that the flip-flop is a positive edge triggered JK flip-flop. Now we will see the operation by considering the different cases of input combinations. This is the circuit diagram. The case 1 we have considered J and K as a don't care, means irrespective of J and K what will happen at the output side we are going to see now. Now here if you observe, the clock is having a low level or high level or negative edge of the clock. It means that as this flip-flop is positive edge triggered, it will not respond to low level, high level of the clock and negative edge of the clock. Therefore output is not going to change at all. Now we will see how the output will not change. Now if we consider clock as a 0 or negative edge, means clock will be 0 for both the cases. Now we know the NAND gate is having at least one input as a 0, so it will outputs a logic 1 output at the output terminal of NAND gate 3 and 4, by which R dash and S dash will become as a 1. So if you observe this truth table of SR latch using NAND gate, when R dash and S dash both are 1, when R dash and S dash both are 1, output will not going to change. Therefore when clock is low level or high level or at the negative edge of the clock, output will not going to change. It will remain in previous state only, irrespective of the JK input. Now we will see the second case in which J and K both are made 0 and now the clock is positive edge, means the flip-flop is now going to work with respect to the variation in the input, that is J and K. Now here J is 0, K is also 0, so at least one input to the NAND gate 3 and 4 is 0, therefore output of NAND gate 3, that is R dash, will become 1, and output of NAND gate 4, that is S dash, will also become 1. Now this is the SR latch to which both the inputs, that is R dash and S dash, are 1 1. So if you observe the truth table again, for 1 1 the output is not going to change, therefore for J K equal to 0, the outputs of the JK flip-flop will not going to change, means for J and K the output is in no change condition. Now we will see the next case, that is J equal to 0, K equal to 1. Now as here clock is positive edge, we are going to consider its value as a 1. Before proceeding the operation, we are going to assume initially the values of Q and Q complement. Here we have considered the values of Q as a 1 and value of Q complement as a 0, means output is in set condition we have considered initially. Since we know the expression for R dash, that is J Q complement clock, its complement, we know the values of J Q complement clock. The value of J is now 0, Q complement is also 0, which we have considered, and clock is positive edge, means its value is also 1, means we will get 0 into 0 into 1, its whole complement. 0 into 0 into 1 will give you 0, and 0's complement will give you 1, so R dash will become 1 now. Similarly, we can put the values of K, Q and clock into this expression of S dash. We will get the value as a 0, means for the given input combination we get R dash as a 1, S dash as a 0, by which output of this SR latch, that is Q and Q complement, will become as a Q as a 0 and Q complement as a 1, which is written from this truth table. Here these are the combinations where R dash is 1 and S dash is 0. So with J0 and K1, output of the flip-flop goes into the reset condition, means we get Q as a 0 and Q complement as a 1. Now in next case, that is J equal to 1 and K equal to 0, again clock is a positive edge of the clock, means its value is also 1. Before proceeding to the operation, we are going to consider the initial value of Q and Q complement as a 0 and 1 respectively, means now we have considered the output is in reset condition or in reset state. Again, by putting the values of J, Q, clock and K into the equation of R dash and S dash, we will get R dash as a 0 and S dash as a 1, by which if you observe this truth table again, for R dash 0 and S dash 1, output goes in a set state, means Q will become 1 and Q complement will become 0. So we can say that with J equal to 1 and K equal to 0, output goes into the set condition. Now we will see the last case in which J is 1 and K is also 1 and clock is 1, means its value is also 1. Now here we are going to consider first the output state as a set state, means Q is equal to 1 and Q complement is equal to 0, and we have the values of J equal to K equal to 1, means both are 1, and clock value is also 1 as it is a positive edge. Now we are going to put these values into the equation of S dash and R dash, here the equation of S dash and here the equation of R dash. By putting the values of respective clock K and Q and clock J and Q complement, we will get S dash as a 0 and R dash as a 1, means input to the SR latch R, now S dash is 0, R dash is 1, means this condition, so the output will get reset. Means initially we have considered the output is in set state, it has converted into the reset state. Means q was initially 1, now it became as a 0. Q complement was initially 0, it became as a 1. So this is how the set state is converted into reset state. Now if we consider initial values of q as a 0 and q complement as a 1, means before proceeding to the operation we have considered the output state is in reset state. Again we know the values of j, k as a 1, clock value is also 1. So by putting all these values in the equation of s dash and r dash, here we have considered the second case in which initially we have considered the output is in reset state. By putting the values of all q, q complement, j, k and clock, we get s dash as a 1, r dash as a 0. Means by observing the NAND gate truth table of SR latch, the s dash 1 and r dash is 0. At that time we get the output is in set state, means q will become 1 and q complement will become 0. Means initially we have considered q as a 0 which has converted into 1, q complement as a 1 which has converted into 0. It means reset state is now converted into the set state. So this is how at every edge of the clock the output is going to shuffle in between the set and reset state. Means initially the previous output status, if we consider it as a reset, it will convert into the set state at the negative at the positive edge of the clock pulse. Again in the next clock pulse, that is in the next clock edge, positive clock edge, again if the output is in set state, it will going to convert it into the reset state. This is how the output toggles in between reset and state. Therefore this condition is called as a toggle condition or toggle state. Toggling means output shuffles in between the two states continuously after every positive clock edge. Now this is the positive edge trigger truth table of JK flip flop. Here we have considered the first case in which the clock is having its negative edge or its negative level or its positive level, output will not going to change. After that we have considered the positive edge of the clock pulse, at that time j and k values are 0, then also output will not going to change. For next negative clock positive clock edge, j and k are 0 1, at that time also output goes into the reset state. For next positive edge of the clock pulse, for values of j as a 1 and k as a 0, output will going to set. And lastly for the next positive clock edge of the clock pulse and the values of j and k are 1 1, then output toggles, means q becomes as a q complement and q complement becomes as a q. Means reset state gets into the set state and set state gets into the reset state after every negative clock edge. Now next we see the negative edge triggered JK flip flop. This operation of this also same, only it works with respect to the negative edge of the clock pulse. The differential circuit is modified, the diode direction is reversed so that it can detect the negative spikes and rejects the positive spikes, and the negative spikes are converted into the positive spikes using this NOT gate, so that this NAND gate 3 and 4 cannot output R dash as a 1 and S dash as a 0 continuously. So to avoid that, the NOT gate is used. After that the operation is same, and this is the symbol of the negative edge triggered JK flip flop. These are the two inputs J and K, these are the two outputs Q and Q complement, and this symbol shows that the flip flop is negative edge triggered JK flip flop. As this flip flop is negative edge triggered, it is going to respond only to the negative edges of the clock pulse. It will never respond to the negative level of the clock pulse, positive level of the clock pulse, and positive edge of the clock pulse. So with respect to that, this is the truth table of the negative edge triggered JK flip flop. Now these are the condition where clock is negative level, clock is positive level, or clock's positive edge. At that time output will not going to change, and for rest of the negative edge of the clock pulses, with respect to the variation in the JK inputs, output will going to change. As we have discussed the operation of positive edge triggered JK flip flop, like that we will get the outputs. Only the difference is the output will respond only during the negative edge of the clock pulse. So we can summarize with this: when J and K both are 0, the output will not change. When J and K both are 1, the output will toggles in between reset and set state after every negative edge of the clock pulse. And when J is 0, K is 1, output gets resetted, and when J is 1, K is 0, output gets set. Thank you.